In health science, health professionals face many instances when they can use one of 3 or more interventions and in which there are few direct comparisons of those interventions. So in these cases, we have focused on direct comparisons or meta-analysis that we know generates a single best estimate for an outcome. That is, we are interested in A versus B, and A versus B have been directly compared. We may, however, be interested in A versus B, but only have randomized trials of A versus C and B versus C. So in this case, we can calculate an indirect estimate for A versus B using the estimates for direct comparisons, A versus C and B versus C. So here we have an example. For instance, we may wish to choose between 2 pharmacological interventions for smoking cessation, bupropion and nicotine replacement therapy. Ideally, we will have direct head-to-head comparison between the 2 treatments. This may, however, not be always available. But in both bupropion and nicotine replacement therapy, these interventions have been compared to placebo. We could make an indirect comparison that will provide some information on the relative effect using network meta-analysis statistical approaches. At this point, I want to make sure that you know that this is important to consider that there are various statistical and clinical assumptions that both direct comparisons need to meet to combine both body of evidence. In this particular example, let's say that our search strategy retrieved 9 RCTs for the comparison between bupropion versus placebo and 19 RCTs for the comparison nicotine replacement therapy versus placebo. You also can see the relative effect estimates and their magnitude of both direct comparisons. And as I told you before, through the applicability of proper statistical methods, we are able to calculate the relative effect estimate and its magnitude for the indirect comparison, bupropion versus nicotine therapy replacement. Let's say that in this case, we also have a direct comparison between these head-to-head comparisons. So in this example, there is 1 RCT. We can get a network meta-analysis estimate by combining the direct and indirect evidence. The combination of these both estimates, the direct and indirect, may enhance precision in the NMA estimate by increasing sample size and thus narrowing confidence or credible intervals. So in summary, we can conclude here that an NMA is an extension of network meta-analysis where it is possible to calculate the relative effect of 2 interventions. In this case, A versus B, in absence of direct comparisons using a common comparator. Also, network meta-analysis enables ranking available treatments. The ranking treatment or rank probability really has become popular as it gives an idea of which treatment is better when it is compared with others for a particular outcome. And using Bayesian or frequentist approach, the interventions can be ranked in an order from best to worst through statistical simulations. So the ranking also can be presented in a graphic or numeric format. So here we have the graphic, a graphic example. The graphic approaches involve examining the area and the curve, indicating the probability of each drug to occupancy a specific rank. There are also other graphic formats that you can see, that you will see, such as forest plot or bar diagrams, among others. In this case, or for this case, we are presenting here rankograms. So let's talk about this example. This graphic represents the ranking of resuscitation fluids in patients with sepsis for the outcome mortality. We can see that balanced crystalloids have the highest likelihood of being ranked first, followed by albumin, gelatin, and heavy starch. For the second rank, balanced crystalloids and albumin still appear most likely, and saline and light starch less likely, but heavy starch now is higher likelihood than gelatin. Looking across these figures, you could make an intuitive estimate of the rankings and the gradient in effect across the treatments. This is another way to present the NMA results in a numerical approach, so that the numerical approach involves the surface under the cumulative rank curve, or SUCRA, where an overall ranking is presented and a single number is associated with each rank. The SUCRA values go from 0 to 100%. The higher SUCRA value and the closer to 100, the higher the likelihood that an intervention is in the top rank or one of the top ranks. The closer to 0, the SUCRA value, the more likely that an intervention is in the bottom rank or one of the bottom ranks. Another format to report rankings numerically is the median and the 90% or with the 90% credible intervals for the rank of each treatment. So here we have the median rank, and it is important that independently of the format that we are presenting the ranks, it is always, you always need to consider that these ranks need to be expressed with, there are certainly intervals, since they have demonstrated a high degree of overlap, particularly between the first 3 top interventions. This applies not also for the median rank, but also for the SUCRA.